Dr. Denis Barbini is experienced general director and has demonstrated history of working in the electrical and electronic manufacturing industry. He is skilled in value stream mapping, failure mode and effects analysis, FMEA, quality management and root cause analysis, along with strong sales and professionals. He's with a Ph.D. Focused on chemistry and materials science, and from the State University of New York at Binghamton. So on a personal note, Denis is a good friend. He is a superb contributor to the SMTA, and he has spoken at many chapter meetings here in Dallas and at all the many of the chapters around. So with that, I'm going to have Jacqueline turn it over to, the screen to Denis, and we'll let Denis take it away.
So what I wanted to start off by saying is, when I look at what's going on now, one of the things I've been participating in and reading about is looking at how resilient we are as an industry. In my time, which dates back to the mid-90s, we've had many challenges. We have economic downturns, shifting manufacturing geographies, pandemics, not just the COVID-19, but also SARS, MERS, but that was the smaller one. We've had to deal with material bans, CFCs, banning lead, going to RoHS. All of these things were very challenging to the industry, and there's always a constant challenge to design and manufacture complex products that are smaller, lighter, more functional. And what I've observed over those couple of decades is that each time the industry creates solutions to overcome the impact and does so with increased efficiency, with innovation that's novel and non-trivial. So we come back stronger and better, and we're able to deliver what our customers are asking for. So that's the good news. We'll get through this. And how are we dealing with COVID-19? When I look at this slide, I say, the first response really focused on the safety and health of the workers, which continues today. And if you look at, our webinar today, this is the very reason we can't get together. We can't, go in the room and sit down and have a beer, like Gary was saying, but we can do it online. Simultaneously, the demands of some companies was to keep going because they're essential and they need to produce at certain rates for ventilators and things of that, products of that kind of impact, while other companies had to ramp down. Either way, this situation has created significant stress on our system. So the next set of challenges is developing and implementing the new reality. For the individual, it's going to be based, like a safety, training in this new reality, having new tools, having the flexibility to, have different shifts or being able to stay safe. Those are the things that really going to be focusing on the individual. The workplace, that's going to change as well. There's all these different states that are saying this is how you can reintegrate, but it's going to limit the person-to-person interaction, safety as well for everybody. That's going to take a lot of training, looking at standards in manufacturing, such as smart factory being, let's say, not just slowly integrated, but it's being forced that in the next year to year and a half, we're going to have innovations that will change the way we manufacture. Organizations such as SMTA and IPC are going to be critical in supporting you and your company. And this is one of the ways that SMTA does it. And then the industry, you look at the supply chain and, the stresses of, running out of components or running out of materials, that can't happen. So regionalizing where we have supply chains is going to be critical. Having, how do we do trade shows and conferences? These are all things that are going to be, discussed in part of this new smart factory and a smart industry. So when this plays perfectly into, the challenges that we have today that have existed for, since electronics started, is we're finding that we want product miniaturization, we want to protect the environment, we have certain applications that demand power, or they might demand the ability to, take some resources. And at the same time, we're concerned about the cost not being too much, but the quality being very high. Where does this blend into? The point of this slide is looking at in the center, materials. If we can get the materials that are proper and using them in a proper way, then we have a good chance of making a good product that's successful at the cost that is what is going to be appropriate. So that leads me into focusing on the rest of the presentation, which is why we control materials and how do we do it. So I'm going to be talking about this the rest of the time and saying, we need to control materials because materials change as a function of time and conditions. Materials are going to exert influence on product quality as well as the cost. So this is why we need to control materials. It's very critical. On the process side, the manufacturing process, the industry has done a great job on focusing and understanding the assembly process. Looking at, how do we do from printing to pick and place to reflow? We have all these different tools to fix the process as well as the design. Failure analysis is a science unto itself and requires a very in-depth understanding of how the PCB is fabricated, rework, surface mount assembly, and a number of different topics here. So in any given factory, you need to have, or a company, you need to have these types of expertise to make sure that you're developing a process that's in control and minimizing your DPMO and increasing your yield. So being able to characterize defects, very critical, but this is already at the end. We need to control the materials up front. So the current assembly process, we can say with confidence that there's been a lot of effort in controlling the manufacturing process, but we know that defects still occur. Solder paste inspection, SPI machines exist because the printer, even though it has a lot of learning in it now, is still producing some defects. So the solder paste goes back and actually can correct it now, can work with the printer to adjust the parameters. Reflow ovens, profiles, are set up with golden boards, and they're able to do a very good job of keeping that process in check. But once again, you have things afterwards, machines afterwards that are dealing with trying to inspect how many defects are on the board. So, and we're getting to the next level of a smart factory. There's that these machines have the capability to communicate to one another and dynamically or on the fly change process parameters to improve yields. However, even after we have all this sophistication, the manufacturer still doesn't have control in the performance of its materials. So, as I mentioned, when this SPI communicates to the printer, you can make some changes here and there, but it's not responding to the material change. It's not responding to saying, okay, my material was, initially started at, in the time 0, but now at time 1 hour, it's changed. It's maybe the temperature, the humidity has changed, or it's been absorbing something, and as a function of the properties, now we're creating defects. So really, we need to understand the, characterizing, monitoring the paste itself in this case. So, material sensitivity. Process controls, as I mentioned, to summarize that part of it, exist to optimize the assembly process, but materials require proper handling and consequent characterization so that we can achieve the best quality. And these images right here are showing that how materials can be sensitive. In this case, coalescence versus non-coalescence on the left versus right. And it's a function of using nitrogen in a reflow process. Well, why is that? Is there something with the paste? Is there something with the flux chemistry? It could be a number of different things. So we need to understand our materials. So in this slide, we kind of assume that we're taking, by taking care of our paste and our boards and our components, we are assuming that everything is consistent and nothing's really changing in the manufacturing floor. But obviously this is not true. Like any other process input, materials you should expect materials to change as a function of usage and time in the factory environment. So when it comes to manufacturing, we all look at how, what is our process window? How tight is it? So that we know where the sweet spot, and we can control our parameters to try and maintain that our assembly that's in the middle of that process window. When it looks at shipping, if we have delays or things are left out or they're not packaged properly, materials are going to change. So how do we know that we're getting the material, when we get the material, that it's in the state that it was manufactured in? And then how long do you keep it on the shelf? And this is a good example for these times, the times that we're in right now. As we move back to going to work and things are opening up and factories are opening up and ramping up volume production, have the materials changed since they were last used? How much inventory of PCBs and components and paste do you have on hand that may have been around for 2 months? So can you still use those, or is it gone beyond the expiration date? So these are things that really are going to be challenging us in the near future, if not already. And we just need to understand how that is going to affect the ultimate reliability, the ultimate quality of the process. And everyone's kind of seen this type of slide where as you go from left to right, from 1 to 6, material problems become pretty hard to diagnose and very costly. So if we can take a material and measure it at block number 1 at incoming and find out whether or not it's fit for use, waiting then or versus looking at after reflow, we can save ourselves a lot of time and money in test and rework. So we're going to talk about that quite a bit. So let's take a step back and breathe. And what I would like to do is, I put a couple of slides in here for reaching out to everybody listening, a question for all of us. As we return to this normal manufacturing, do you know if your materials are going to be the same or if the materials have changed? Are you going to be able to use these materials? Of course, there are many different materials. I'm going to be focusing on paste, but there are many that could be of concern to you. And can you answer the question, how will material changes impact yield, DPMO, rework, you name it? It's going to affect your factory and its process, its manufacturing process. So once again, I'm trying to say and communicate that we need to really control our materials and characterize it. So in this case, in collaboration with that, as you go down the process, it becomes harder and more costly to fix problems. We know that 50 to 70%, depending upon who you speak to, of defects in surface mount are related to the process of printing. And then as a subsequent 30 to 50%, almost half of the manufacturing cost is due to test and rework. So once again, we do a great job of understanding the printer and the parameters that are important. We have SPI, and now we have a method right here that the manufacturer tells you how to store your paste. And it gives you the temperature, it gives you a number of different things that you should do. And then on this page, you look at, once again, first in, first out. Paste should be brought to room temperature for 3 to 4 hours. Never use or should not use a mixer, things of that nature. So these are just guidelines to say if you do this, then your paste will be fit for use. But what is the real condition of the solder paste, of your solder paste? So when Insituware looks at, how do we track a paste fitness for use? Right now, as it currently exists, the paste supplier provides conditions for storage, preparation for use, and then actual use. The factory, you have best practices. You have a manufacturing flow that you have to use in order to get the best yield and the best DPMO. This is based on experience, based upon design and controls that the company has put in place. There are systems that exist that are tailored to track all materials, not just paste, but from receiving to use on the factory floor as it's traveling through the manufacturing process. This gives the customer or the manufacturer traceability of, in this case, the paste container. And then you have the combination of printer SPI, combination of reflow AOI systems that provide feedback to improve process parameters to mitigate defects. Okay, so that's what we do today in most conditions, most factories. But I just went through a whole bunch of things, but are we really monitoring the paste itself? The answer is no. And that's why we're looking at the need to revolutionize the way we control materials in manufacturing. And how are we going to do this? We're going to do it by taking material science and material characterization techniques that started in the laboratory and bringing it to the manufacturing floor. Sounds pretty easy. It's very complex, but this is something that we've pioneered in doing so. So in this case, to drive home the point that materials change over time, this is a simple rheology experiment where the x-axis is looking at, time zero. You put paste on the stencil, initial time zero through 12 hours, and you're looking at how the paste is going to recover. And we start about an average of 65%, and we go down to, let's say, 45%. So you have a 20% decrease in rheology. Now, how is that going to cause, is that going to cause defects? Well, the material certainly changed, so that's going to impact the paste transfer through the stencil and then ultimately cause a number of defects. So, once again, that's why Insituware did the research, figured out how we can help the industry in measuring solder paste at the manufacturing floor within 3.5 minutes. So it's our vision system. I'm not going to talk too much about that. I just want to really focus on the technology. If this is your line, we see there's more than just 5. We kind of done like about 18 different ways of where controlling your solder paste or monitoring can be made, and we're learning from customers like yourself how this could be used to improve your process. But if you look at number 1, so we take a measurement, and I'm going to talk about that in a moment. We're going to be looking at incoming materials. So you get a shipment from your paste supplier. You can do a test and say, okay, this is the baseline of the material, and it's representative of the lot. And then we can track it lot to lot over time to see if there's any variation in the viability. And if anything happens, then you can contact the paste supplier right at the start without even using it. This is one of the things that talking about, if you manufacture the entire product, but you never measured it at incoming, that could be a major problem. Number 2 is that before you commit the paste to the factory floor, you can, once again, make a measurement of the paste and then understand the storage conditions and the viability in the current environment. Current environment can mean relative humidity and temperature. You can imagine a factory here in New England versus a factory in Texas or in Mexico or wherever it is. You have different humidity levels, different temperature in the factory, and as a result, the materials are going to behave differently. So, and then number 3, you're at the stencil printer, and you can measure changes in solder paste during the printing process, so that that maybe over an hour or 2 hours you're good, but maybe longer than that there might be some issues. Or you might want to determine how often do you need to clean before you have defects using this kind of a measurement. Number 4 is actually pretty interesting, is that depending upon your environment, once again, I'll use the New England model because that's where I live. It says here, we can adaptively change time on the stencil based on the current state, meaning in summertime here, it gets very humid. in wintertime, it's very dry because we're heating the environment up. So based upon the humidity, we know it's going to change the quality of the material, and it's going to change the way how effective it is. And as a result, you may only have, let's say, 8 hours on the stencil in a very wet environment, or you can have 12 hours in the wintertime because it's drier. So you really have the ability to change your process, optimize your process by understanding the material. And number 5, once again, it's a very similar situation. Is let's say you are printing and you're placing components during the day, but it's really too humid to do the reflow process. You wait till the night so things cool off and you can reduce the temperature, reduce the humidity, and then you process the boards. Is your paste still viable, or has it gained too much or picked up too much humidity? Has it been damaged, or has it been baked out too much? That's another measurement that can be taken to understand if you're going to get defects in controlling your solder paste. So these are just 5 examples of where measurements are being taken to help the manufacturer develop a robust process and minimize defects. So what are we measuring? It depends on if it's water soluble or a no clean. But for water soluble, number 1 here is the powder reactivity coefficient, the PRC. This is due to the aggressive nature of the flux-powder interaction. So it's very aggressive. We're trying to remove the oxides from the metal surface. And in water soluble, that happens very quickly. So we're measuring the PRC in water soluble. And no clean, the activator package is much different. So it's not as aggressive. This way you don't have to wash it. And so as a result, we're looking at the ion mobility within the bulk of the flux. So that is going to be at a slower rate, and it happens in the bulk flux media, which is different from the activator interacting with the metal. So how does this work? It's electrochemical analysis. And what we're doing here, you see on the left-hand side, these little deposits of solder spheres and paste. On the right-hand side, top right, you see basically electrochemical schemes. You have a working electrode on the left, reference electrode on the right, and you have the metal as a resistor. It's actually, you have the resistor there, and then the flux itself, the flux media, it has capacitance and resistance. And we're looking at below the reaction of the bulk media, which is on the right-hand side, the blue spheres, and looking how fast those ions are moving, versus for no clean, for water soluble, we're looking at what's happening between the surface of the metal, removing the oxides with the activator. So depending upon the paste type, that is what we're looking at. And this talks about homogeneous materials. These are the bulk properties. So this is over to the right-hand side of that sphere with the blue molecules. And the heterogeneous is basically the reaction rate between the oxides on the metal and how fast that interaction is taking place. So what we're trying to do here is applying electrochemical understanding to printing performance. So a little bit of science there. But what does this mean in terms of manufacturing? Basically, we're looking to make sure that we have the concerns in the manufacturing process of maybe forming slumping, skips, smears, solder balls, and then in soldering, poor solderability, undesirable residues, and consistency issues at incoming and in process. So once again, we're trying to determine, is the solder paste fit for use depending upon its chemical formulation as a function of time and conditions. So I showed this slide before, but you're seeing now how this is an important property. And as the paste rheology decreases, recoverability decreases, which correlates to the number of printing defects. So in this case study, what we have done is to look at defects as a function of paste fitness. So using SPC type of analysis here, we're overlaying something that is, below the yellow line. You're in control. So you're making your measurements of the PRC, the powder reactivity coefficient, and anything below, any number below that yellow line is in spec. If it goes beyond, you are in a place where you might get some defects. But once you get above the red line, around 3, in this case, you start to see skips. So once again, this is like you would do in any other machine, is that you have these control limits set up that will tell you whether or not the process is in control. Now we're taking our material measurement and we're doing the same thing, relating it to the defects. So now this is the missing piece of the assembly process. We're combining the knowledge of the machines with the knowledge of what's going on with the paste. And we know that there are many properties that affect the paste itself. These are type of things that are done at the paste supplier or in the lab, where you're measuring the rheologic properties, the bulk ionics, the solubility. You're not doing this on the manufacturing floor. So that's what we're doing. We're taking these types of analytical tools and bringing them to the manufacturing floor and giving you very rapid results to let you know right away whether or not this is going to be fit for use, your paste. So there are data sheets that we provide for a given paste. This slide over here shows a tin lead, no clean. I'll look at sensitivity to humidity. So this is no clean, so we're doing the flux coefficient measurement. The bottom left, there's 2 lines, and you can see that the flux coefficient for 60% relative humidity is, let's say, less than half of at 35%. So this paste will behave very differently at 35% humidity versus 60% humidity. How does that affect your reliability or your performance or paste transfer, and ultimately product performance and yield? Right. So once again, in measuring, being able to measure what the flux coefficient is and making sure that it correlates to the defects that you're observing, you can put these control limits in place so that any operator can just make a measurement, plug it into this, the information system, and say this is either out of control or in control. And that will be on the device. The device will tell you that. So these are the important things. If I look at the bottom right of this, I want to translate the paste properties to the fitness for use. Ultimately, the bottom right is this process control limits that we're trying to achieve. And being able to say, if your process window for a given paste at a given humidity and temperature, you can set it so that you make sure that that paste has a value that's somewhere in that between the limits, the yellow and the red. That's where you want to be. Same thing you would do, as you would do in a reflow oven, whether time above liquidus or overall time that a component can, how much heat a component can observe. So these are things that really kind of put together all the attributes of a manufacturing process that gives you the power to optimize and get the best yield. So I just wanted to kind of let you know that it's not black and white. Solid paste failure is not something that's easy to do. And what happens over its lifetime? This is PRC. It has 4 different curves you can see, and they're all based on different hours. So 0 is the blue bottom, and 24 hours is the orange all the way on top. And what you're seeing is a much different behavior of the paste itself. This is why it's important to measure and characterize what's going on in your paste. We also, using this type of technology, we're able to classify what a no-clean flux looks like, what water soluble looks like, based upon the chemistries that are being used in industry. So a lot of analytical tools available to say these are every paste is unique, but they fall into certain categories. And this is what it looks like. So depending upon if it's tin lead on the left, SAC 305 on the right, water soluble on the top, no clean on the bottom, you can see that they all fall into a certain type of behavior. They're all different because different solid paste behave differently. It's made up of different packages and different chemicals, and as a result, they behave differently at time zero. Once they're exposed to the manufacturing environment, these behaviors change, and that's what we're measuring. We're seeing what the change is and whether or not it's still fit for use. So, I'm almost wrapping up here. The vision system is shown right here. We're able to, inspect and characterize incoming materials. When there is a problem, you can understand whether or not the paste, in this case, this material, the paste, was part of that problem or it wasn't. And then ultimately, you want to be able to monitor the process, not just on day one, but throughout the day or over many days. This way, you have complete traceability of what's going on your product development. So I'm going to, a couple of things. Our family of insights, meaning what materials are we going to be measuring? Today, I just spoke about solder paste. We're also looking at conformal coats. We're all looking at cleanliness, looking at residue characterization. So we have a roadmap using the same device to look at other materials that are of interest to you and to the industry. So one day when we have time to talk about other material characterization, we'll do so. But this is right now our first product release, was released at Apex, and is working and evaluating these days. So I'm going to finish. I'm going to wrap up here with a question once again for all of us. Material characterization and material control is critical to optimizing the process, and I hope that I've driven that home and you understand it. I'd be happy to see your feedback and your thoughts on this. But we believe that real-time understanding of materials that's being used in the manufacturing process is the only way to provide objective evidence, complete traceability, so that you can achieve improved efficiencies and quality with a minimal resources. And with that, I would like to know, and I know my colleagues would like to know as well, what materials would you like to characterize and control in your manufacturing process? What do you think you need to make your product more reliable, better yield, at lower cost? So I'm going to leave off with that by saying thank you very much to everybody, to the Dallas chapter, to everybody online watching. Thank you to all my colleagues for all the work that they do and supporting us during these challenging times. And my email's there, so if anybody would like to reach out, I'm happy to follow up with you on any given question. So with that, I'll transfer it back to Gary and Jacqueline. Thank you guys very much for having this, and thank you, everybody.